Welcome to the fourth video on steady state analysis. This particular video is going to look at how we can remove the offset in the steady state of a closed loop. First, let's remind ourselves what we know already. We assume students are familiar with how to calculate the steady state offset for a simple feedback loop of the form shown here, with a controller M of S and a plant G of S, and nothing in the feedback path. We're going to assume constant set points of the form R of S equals 1 over S. Here we're using unit step for convenience. You can change the magnitude, but it really doesn't change the detailed analysis. And what we want to do in this video is ask ourselves, how can we remove the offset? How can we make sure that the steady state for the error signal, the difference between the target and the output, is 0? First, a few reminders of the formula we're going to use. For a simple loop diagram like this, then the error can be calculated as 1 over 1 plus gm times r, where r of s is something like a over s. We're going to use a equals 1. And if we apply the final value theorem, then what we find is the limiting value as t goes to infinity of e of t is 1 over 1 plus g of 0 m of 0 times a. And what we showed in the previous video is clearly that if g of 0 is bounded and m of 0 is bounded, then this error is always non-zero. What do we need to do to eliminate the steady state offset then? Well, let's write this final value theorem down just a little bit more carefully. So what we've actually got is the limit as t goes to infinity of e of t is the limit as s goes to 0 of 1 over 1 plus g of s, m of s. And again, I've assumed that the target is 1 over s for convenience. Now, in order for this limiting value of the error to go to 0, clearly we need the limit as s goes to 0 of 1 over 1 plus g of s m of s equals 0. And this implies, the most significant observation, is the limit as s goes to 0 of g of s m of s has got to be infinite. That's the only way you can get a 0 out of this formula, is if you make the denominator infinity, and that means that either the limit as s goes to 0 of g or m has to be infinity. So we'll clarify that here. For a simple feedback loop, the steady state offset can be 0 if and only if either of the following holds. The limit as s goes to 0 of g of s is infinity, and I'll put in the middle here, or, it doesn't have to be both, the limit as s goes to 0 of m of s is infinity. Now, you'll notice I've also used the word can. That doesn't mean must, okay, because you may have an unstable closed loop with either of these two conditions. So a transfer function has an infinite gain if and only if it contains an integrator. You will have noticed that in one of the earlier videos on gain. So what we can do now is we can translate the observations in these two boxes here to actually saying we can get a 0 offset if and only if we include an integrator. Okay, so if you want to get rid of steady state offset, there must be an integrator in the forward path, and it could be in the compensator or in the plant. It could be in either, doesn't matter which. However, and we'll reiterate this again and again, this is only true if the closed loop is stable. Now, just to reiterate this issue about the integrators, find the system's steady state gains for the following transfer functions, and I'll write them down very quickly. So in this case, g of 0 equals 2. I'm sorry, the screen's behaving a bit funny here, I don't know quite why. In this case, g of 0 equals 5 over 3. And then in this case, you'll see that we've got an integrator, there it is, in the process, or a pole at the origin, and therefore g of 0 is going to be infinity. And finally, if you look at the one down here again, we have an integrator in the system, so again g of 0 equals infinity. So this slide is simply to remind you that the only way you can get the limiting value as s goes to 0 of g of s to be infinite is if you have a pole at the origin in that transfer function. Okay, some examples to look at now. For this particular example, we've given that this closed loop is stable. You'll see in the blue box it says, I'm telling you it's closed loop stable, and it says find the steady state offset for the following system. Now what I can do is I can write by inspection. Okay, so I'm writing that by inspection, the limiting value as s goes to 0 of g of s equals infinity. You can see that because it includes an integrator, and therefore offset equals 0. Now, if you're doing this in an exam, you might first be required to actually put in the formula that the offset is given by 1 over 1 plus gm, limiting values obviously, and then show why putting in infinity allows you to get a 0. But we've already done that, so I'm not going to write it all over again. And here's a plot to demonstrate the fact. So I've calculated the output, and here it's plotted in blue. I've overlaid the target in red, and you can see clearly the output converges to the target. There is no offset. So by including an integrator, I have eliminated the offset in the steady state. Another example. Find the steady state offset for the following system controller pair. Now you'll see this particular G of S does not include an integrator, so we're expecting there to be a non-zero offset. So if I write the formula, 1 over 1 plus G of 0 M of 0, or because I know what G of 0 is, I can write 1 over 1 plus, now G of 0 is 6 over 8, which is 0.75, so I get 0.75, and I'll just put M because M is a constant in all these cases. So here, if I put M equals 1, I get 1 over 1.75. If I put M equals 20, I get 1 over, that's going to be 15, isn't it? 1 plus 15. And if I put M equals 100, I get 1 over 1 plus 75. Now, the clear thing to notice is that as M increases, the error, or the offset, gets smaller. Okay? So as M increases, the offset gets smaller, but it's still not 0. Now I want you to remember this, because if you look at this G of S, we're going to use the same G of S, or nearly the same G of S, in the next couple of slides. But the key point here is I've increased M, I've made it bigger and bigger and bigger, but still I get an offset. But as I increase M, the offset has got smaller. Now look at this example here. I've got 6 over s, s plus 2, s plus 4, and you'll see it's the same as the previous example, except I've introduced an additional s, an integrator. Now this box keeps flashing at us. The software is obviously not very happy, and it tells us confirm closed loop stability first. That's what I need to do. So if I write down the closed loop pole polynomial, is PC equals 6 plus s, s plus 2, s plus 4, and I'm not going to actually calculate those poles. You can do that in your own time, and you can verify all poles in left half plane. I'll let you do that by yourself. I've checked already, and indeed all those poles are in the left half plane. Having done that, I can therefore say includes an integrator, and you can see that, and therefore offset equals 0. I don't need to do any number crunching at all, because the integrator's there. I know the offset will be 0 as long as the closed loop is stable. What about the next example? Again, you'll see I've used the same G of S, almost the same anyway. It's got the same pole positions, but in this particular case I've moved the integrator to the compensator, to M of S. Now that makes no difference, because you remember in the earlier slides we said either the compensator or the plant has to include an integrator. So in this case, I've still got an integrator, but the main difference is I've now got a gain of 20, whereas in the previous slide I had a gain of 1. So now let's calculate the closed loop pole polynomial, and I get PC equals 120 plus S plus 4, S plus 2, and you will find this has right half plane roots. Okay? Closed loop is unstable. So there's an interesting factor, isn't there, or observation. By making the gain of the compensator up to 20, and let's not worry too much about the integrator, I've made the closed loop go unstable. And yet you'll remember, before I put the integrator in, I was making the gain 20, 100, and the closed loop was still stable, no problem. The offset was getting smaller, not 0, but I could make the gain very large. But now that I've introduced the integrator, once I start increasing the gain, the closed loop has become unstable. So you might have said, oh, I'll use the integrator and get rid of an offset, but it's not worked because you've made the closed loop unstable. One final example then. Again, first thing to do is check for closed loop stability. So I'm going to write down PC equals 100 times 3S plus 1 plus S into S minus 2, S plus 5, and verify all roots in left half plane. Now again, I've done that myself already, but you need to do that. Verify that all those roots are indeed in the left half plane, and so this is closed loop stable. Once you've done that, you say, aha, there is an integrator, and therefore 0 offset. I don't need to do any more computation. In fact, the hardest computation in this case is verifying that the closed loop is stable. But once I know it's stable, the offset looks after itself. So a conclusion. For simple loop structures, the system's steady state offset to a unit step target can be eliminated if either, and that's the key thing, either the controller or the system includes an integrator. However, that's only true if the closed loop is stable. And the final thing you've noticed is that integrators can be destabilizing. So once you include an integrator, as you start ramping up the gain, it's quite likely in general, certainly in practice, that the closed loop will go unstable. So the inclusion of an integrator limits the value of gain that you can use otherwise.